Hello, mathophiles. In this episode, we're going to show that Z mod NZ is a group under addition. Z mod NZ are the equivalence classes from modular arithmetic modular n. So let n be a positive integer greater than 1. We're going to let Z mod NZ be the set of equivalence classes. That is, we write that it's equivalence class is of the form I, where I is an integer, so every equivalence class is in this set. Here we recall that the equivalence class of I is the set of all integers k such that k is congruent to I mod n. We recall the definition of our equivalence relation. That means that n divides k minus I. So it's a set of all integers such that n divides k minus I. Finally, worth noting that this set is actually a finite set because the equivalence classes are the equivalence class of 0, 1, 2, up to n minus 1. Why is this true? Well, because one can always check that for any integer k, by the division algorithm, it must be of the form qn plus r, where r is less than or equal to n minus 1. But by our definition, that means that k is congruent to r mod n. Right? Because this part here, this quotient times n, that's just a multiple of n. So k minus r is a multiple of n, so k is congruent to r mod n. So in particular, every integer is congruent to one of these possible remainders. And so this is a complete set of equivalence classes. So I'm going to turn this set of integers modulo n into a group, and here's my definition. A plus b, the sum of the equivalence classes is just going to be the equivalence class of a plus b. Now, before I can prove that this structure with this group operation, this addition operation is a group, I actually need to show that this addition operation is well defined. What do I mean by that is that, well, this formula, as I've written it, actually depends on a and b. But, the equivalence class of A includes a lot more things in it than just A, and the equivalence class of B includes a lot more things in it than just B. So this formula is saying take something in bin 1, take something in bin 2, add the two things together, and the sum of the bins is the bin of their sum. And it's not clear that what you get is uniquely defined. And to show what I mean, I'll show it by a bad example. I'll show you an example of something that's not well defined. So let's take our rational numbers, and let's define the star product of these two fractions to be the sum of the numerators. Well, let's compute this star product of 1 over 1 and 2 over 1. Well, the sum of the numerators is 3. On the other hand, if we compute the star product of these two fractions, the sum of the numerators is 2 plus 2, that's 4. But we have a bit of a problem here, because 3 is not 4, so these two operations are not the same. But these 1 over 1 is equal to 2 over 2, they're equivalent fractions. So I claim that I tried to define an operator on pairs of fractions, but it's actually not well defined because it doesn't depend just on the fraction, but how I chose to represent the fraction. And so the point is that in order to be a well-defined function on fractions, it isn't just a function on these pairs of integers, but that if I replace the fraction with an equivalent fraction, I get the same answer. And the point is that I need to show the same thing for my congruence relation, that if I replace a and b with equivalent integers, in other words, congruent integers modulo n, a plus b is congruent mod n. So in other words, if A is congruent to A prime and B is congruent to B prime, I need to show A plus B is congruent to A prime plus B prime. That allowed me to conclude that my addition operation is well defined. It did not depend on my choice of representative of my equivalence classes. Or to use my fraction analogy, it didn't depend on how I chose to write the fraction as a numerator over a denominator. So we want to show A plus B is congruent to A prime plus B prime. That would allow us to conclude that this summation, which I defined to be this, is actually equal to this one, because they're the same equivalence class. So my addition operation ends up being well defined. It doesn't depend on what representative I pick from the first class and what representative I pick from the second class. I, of course, put a check mark here because we actually already showed this fact. And so because this fact is true, our definition is well defined. So now we get to the main claim of this video. Z mod NZ is an abelian group. Well, what does that mean? What are the elements of the proof? Well, we need associativity, which means for any three integer or elements, the sum is the same regardless of how we do the parentheses. I should say the ordered sum, since order does technically matter in property 1, associativity. Note here, because I'm working with addition, I've written the axiom using plus signs instead of multiplication signs. What's the next property I have to show? Oh yeah, the identity. There exists some element E, such that for all A, adding E to A gives me A back again. Finally, I need inverses. Because I'm working with an additive group, inverses are actually negatives. For every A, there's a negative A, such that A plus negative A gives me the identity back. Finally, if I'm going to claim it's an abelian group, I have to show the commutative property. For any pair of elements, A plus B is equal to B plus A. Note, since equivalence classes correspond to equivalence classes of integers, we'll see in the proof that oftentimes I'll look at integers instead of elements. Technically, this was inappropriate. These should all have square brackets. So now let's do the proof. Okay, as a first thought, remind ourselves the first thing we want to do is this claim. We have an additive group. We want to show associativity, which is this claim. For every triple of elements, these two products are equal, where we've just moved the parentheses. So first we show that addition is associative. So note this red stuff is not in the actual proof. This black sentence is. So what do we need to do next? Well, this is the claim we want to prove, and it's a universal quantifier. The first thing we want to do is consider three arbitrary elements in the group. Since the group consists of equivalence classes of integers, what we want to do is consider three arbitrary integers a, b, and c. So we're going to let a, b, and c be integers. Then what do we want to do? We want to do this calculation in the group and hope that we end up with this calculation. So start. Here's this calculation in the group with the parentheses on the left. Equivalence class of A plus the equivalence class of B, parentheses, plus the equivalence class of C. Well, there's not much we can do, so let's apply the definition of addition inside these parentheses. This sum is the equivalence class of the sum of A and B. And we see there's not much else we can do. We have a sum of equivalence classes, and there's nothing we can do inside here, so the next step should be to apply the definition of addition here. So we do that. The definition of the sum of equivalence classes is the equivalence class of the sum. Note here that order matters, so we had the parentheses again. But now we see we've made some progress, because we now discovered that this calculation is actually the equivalence class of this sum of three numbers. But these are integers, and we already know associativity holds for integers under addition. So we can move the parentheses over. A plus B plus C is equal to A plus B plus C. And now we seem to be stuck, but then we remember our goal is to get to this. And what is this really? These should be square brackets. So this is the equivalence class of A plus the equivalence class of B plus the equivalence class of C. So somehow we need to replace this equivalence class with sums of equivalence classes. There's not much we can do there because of this parentheses. So there's nothing we can do inside the parentheses, so we work outside the parentheses. And we recognize that this equivalence class is actually equal to the sum of these two. The sum of the equivalence class of A plus the equivalence class of B plus C. Oh, well, that's progress, because we can replace the equivalence class of B plus C with the sum of its equivalence classes. And that's precisely what we do. And we see that we get exactly what we wanted. And every time I see this without the explanations, it looks kind of weird, because it just looks like a bunch of random symbols. But when you go through the logic at each step, it actually makes some sense. This first term is the sum of three equivalence classes. This next term is the sum of two equivalence classes, one of which is represented by the sum of two integers. And this next thing is one equivalence class, whose representative is the sum of three integers, and so on and so forth. So when you go through it and you understand what each of these symbols mean, you realize they actually do mean something slightly different. But we see addition is associative, which is exactly what we want to show. Why? Because we took three arbitrary elements, and we showed that the order of parentheses didn't matter. All right, the next step is to prove we have an identity, which means that there exists an E such that E plus G is equal to G. Well, we already know what it should be. It should be the equivalence class of 0. So now we show that the equivalence class of 0 is the additive identity of Z mod NZ. Again, the red type up here is not in the proof. This black font is. So what is left to do? Well, we're claiming that this is the correct element. So what do we have to show? We have to show it has the right property, which means we need to take an arbitrary group element and show this calculation works. So let A be an arbitrary integer, because an arbitrary equivalence class is the equivalence class of an arbitrary integer. Then we just do the calculation. 0 plus the equivalence class of A is the equivalence class of 0 plus A, which is just the equivalence class of A. Oh, look, that's exactly what we wanted to show. So we can write down, hence, the equivalence class of 0 is the additive identity of Z mod NZ. Well, we got the associativity down and the additive identity. So next we got to look at the negatives. So for every element in the group, it has a negative. I say negative because we're working with addition. So when you add something to its negative, you get the identity back. What is the obvious choice for a negative here? Well, the equivalence class of a negative. So now we show that our group has additive inverses. Let A be an arbitrary integer, because that's what we need. Now, given the arbitrary integer, we can define the negative that depends on it. Well, let's define it to be the equivalence class of negative A, because that's what we think it is. Now we just have to check that this calculation works. So negative equivalence class of A plus A, well, oops, I skipped a step. Let's include that missing step. By definition, that's the equivalence class of negative A. And then by definition of addition, that's negative a plus a, which is the equivalence class of 0, which we already showed was the additive identity. So we see that our group has additive inverses. So I've been using the word group when I technically shouldn't have, but now we see that it actually is a group. It's associative, it has an identity, and it has inverses. Of course, if we want to claim it's an abelian group, there's one last property to check, and that's commutativity, which means that for any two elements, their sum is the same no matter what order the elements appeared in. So, finally, we show addition is commutative. Take two arbitrary integers. What do we want to show? We want to show the sum of the equivalence class of a plus b is equal to the sum of the equivalence class of b plus a. Well, we know this is the definition of addition. We also know that addition of integers is commutative, so we can replace a plus b here with b plus a, which is exactly what we do. And then we see that the equivalence class of b plus a is the sum of the equivalence class of b with the equivalence class of a, which is exactly what we wanted to show. Given two arbitrary equivalence classes, a and b, you got the same sum no matter what order they appeared in. And then we add the remaining sentences. We've managed to show that the addition operation is commutative. And so now we add the final sentence to the proof. We can conclude that this is in fact an abelian group. It's associative. Multiplication, or addition in this case, was associative. There was an identity, there were negatives, and the addition operation was commutative. And so here was a good example of a proof that something, an additive group, was abelian. And so we see the main difference is working with plus instead of times and working with negative instead of inverse.